Launch success, Crew-1 blasts off from the Cape as SpaceX helps NASA officially get back to launching from American soil over 10 years after the shuttle retired. On the move, scientists now theorise that mysterious dark matter is hanging around at the outer edges of spiral galaxies, not in the centre. New theories about Hawking radiation, as research suggests something of you would survive an encounter with a black hole. It's Tuesday, November 17, 2020. Those stories plus the headlines on this edition of Talkin Science.
Beaming around the world with the latest science and space news on Facebook Watch, YouTube, and wherever you get your podcasts. This is Talkin Science with Dr. Brad Tucker and Matt Miller.
And it's a very happy Talkin Science Tuesday to Dr. Brad Tucker.
How's it going?
Really good, really good. November is almost done now as well. I remember when it first started and we said, wow, 11 months are flying by.
Yeah. The end of the year is around the corner, let's say that.
It absolutely is, and there's so much to look forward to next year. So much has happened this year, and there's still plenty of stuff to talk about today. We've got a jam-packed show, so looking forward to jumping into that with you. But of course, before we get there, got to mention the social medias. Brad, you're on Twitter at btucker22 and on Facebook, Dr. Brad Tucker. I'm on Twitter at Miramat86. And of course, Trekzone all over social media. Just search for Trekzone. Brad, let's dive into the headlines.
Talking Science Headlines.
And Brad, the Aussie Space Agency has chosen a new head to replace outgoing Dr. Megan Clark.
Enrico Palermo, who's coming over from Virgin Galactic, actually. So he originally was or came from Perth. I think he went to UWA. Has been working for Virgin Galactic and really the spaceship manufacturing side, and will be the second head of the space agency after Megan Clark's stint finishes at the end of the year.
I think this is incredible that we have an Aussie. He's going to be coming home to assume this post. We have an Aussie with this experience. He's worked at Virgin Galactic. He had a scholarship from the European Space Agency and studied at the International Space University in France. So he's certainly very suitably qualified.
Yeah, look, it's coming from industry background, I think will be quite good. The Australian Space Agency in Australia has been trying to really focus on working with private companies and developing that technology. So it'd be good to have someone from the inside, so to speak, to help further the goals in Australia.
Now, Southern Launch Australia has announced a new cooperation agreement with Germany's space agency, DLR, that'll see it used as a base for German rocket tech.
Yeah, DLR has been working with quite a few people in Australia, including us, interested in obviously reaching other areas. And, one of the things that we talked about when the Canuba test range where Southern Launch was launching from was just having that ability to launch from the south and launch, as far south as you can in remote areas. And, with Europe, they're pretty much stuck going to French Guiana for the most part, unless they go to a different country or partner. So Australia represents an easy partner with lots of room to work with. So it'll be exciting for everyone.
Well, part of this cooperation is the Canuba test range, as you mentioned. Now, we've talked about that previously, and launch director Alex Lanossi has been on the show as well. It's a fantastic location, far from anyone. And as you alluded to there, there's no place like it in Europe at all.
That's exactly right. And it's the same thing when people have talked about the Nhulunbuy test, center up in the Northern Territory, even in Queensland. We just have open, secure spaces with, the weather that works. And it will be interesting to see how this develops in the future, because I think that was always one of the goals, is not only being able to launch our own stuff, but being that center for other people to come in and use as well. And again, Nhulunbuy has been working with NASA for sounding rockets. So and again, it's something where a few years ago we never really thought we'd be seeing rocket launches anytime soon from Australia. Now it seems like it's going to be a big part of the next 10 years.
Now, meanwhile, in Sydney, Clearbox Systems has signed up with Boeing Defence Australia to collaborate on next-gen Satcom technologies.
Yeah, and again, it's another one of these partnerings with Australian companies, Clearbox being essentially a small sat group that fell out, I think, of the University of Sydney or UNSW, and really trying to develop packages for communication satellites, something that we've done with the Australian Air Force, but now looking at going obviously to that private sector that works in a large way, especially not only with Australian defense, but the US defense as well.
Now, previously, all this tech was really big, bulky, expensive, but now thanks to advancements in computers and CubeSats, it's a lot more achievable to be able to do this on quite a tighter budget.
Yeah, and it's all about payload size. The smaller and quicker you can make it, the cheaper it ends up being, the easier it is to launch. So there's lots of benefits of going this route instead of just gigantic satellites. And it's finding the right balance between being small enough and too small, and also the technology on board that satellite, that miniaturization. And again, this is something Australia was always going to be looking at, leading, something we were always doing a lot of, small sats, and it's going to pick up even more.
Talking science, stories of the week.
And yesterday, Crew-1 launched from the Cape, and NASA is back to launching American astronauts and others from American soil.
Yes, it was a highly anticipated launch after Demo 2. Had some weather delays, so they pushed it back today, but this was already pushed back from October when they were supposed to go up, but that was delayed for technical reasons. But they looked like they had a pretty perfect launch yesterday, and are safely on their way to the space station and should be there by the time people are listening to this.
Yeah, absolutely. So we're recording the morning's release in the evenings, and in the middle of all of this today is the planned docking of Dragon to the International Space Station. It's a little longer than the last Soyuz mission that I think only took a few hours to get up there, but I was researching this one, and there's a lot of things that have got to fall into alignment to get up to the space station fast. Sometimes it's just better to fly around the Earth a few times.
That's right. It's all about the working of the orbits, what's going on the space station, where they're docking, all sorts of things. And the last Soyuz one was a fairly impressive record in terms of speed, getting up there. And, in this case, as you said, sometimes taking your time is not a bad idea in this case.
And we've talked about this in the past. It's private companies taking over, dare I say, the mundane tasks of maintaining a space station and also getting astronauts further into the solar system, something that frees the space agency and the space agencies up for really creating these creative missions. So NASA's come up with Artemis and has tasked the private companies to come up with the ways of making it all happen. So this is a fantastic result for SpaceX. Finally completing that mission that they set out to do, almost 10 years ago, to have a crewed Dragon flight.
Look, that's exactly right. This is something that NASA, the U.S. government, and Elon Musk wanted to do for 10 years, or not quite, but almost. Ambitious would be putting it lightly, something that really wasn't possible. Not only just a private company, but SpaceX in particular, which was kind of new at the time. The idea of reusable rockets building into this thing, that the U.S. would be able to focus on other things. And now we're seeing the benefits of all this work, allowing private companies to focus on these closer, nearby, more regular tasks, so the other groups, as you said, can focus on those bigger, challenging problems. And it's just in service now, and now it's not going to be as big of a deal anymore. And that's kind of a nice thing, to so to speak, that this ability can happen. And now that you can launch multiple groups of astronauts, that means there's more countries, more astronauts, more experience, more experiments, more science. So it's an exciting time all around.
Dragon's crew complement of 4 is one more than Soyuz, who can take 3. So, as you say, this is a really good thing to be able to now send up 7 astronauts pretty much, every few months is an incredible opportunity. Is going to increase the workload that the space station can achieve.
That's right. Kind of being able to stagger, usually their 6-month missions, being able to stagger it in groups of, every 3 months. And again, you having a lot more people, a lot more equipment, and that means more people to work on things. And a great example is the Bartolomeo platform, which is a new part of the space station to be used by Airbus to host different experiments. By having more astronauts up there, they can work on it faster. In fact, that work was paused, waiting for the rest of these astronauts to arrive. So it will just accelerate the process. And again, it means chances for other countries to participate in. And a great example is on this last mission, there was 3 Americans and 1 Japanese astronaut. So it won't just be seats really of the Russians and Americans, because in the past with 3 seats, you had to have at least 1 Russian. There at least was always 1 American. And then there was the 3rd seat, which was usually either another Russian or American. In this case, it's a lot easier for other countries to send people up.
It absolutely is, and looking forward to Crew-2, which is already slated for next year. And the brilliant thing with that mission is that they're going to be reusing the Falcon 9 from this mission, which was successfully recovered.
And that's, the whole goal of SpaceX is, again, to make this as reusable, and where the market, where the technology, where the science and engineering is moving. And that's a great thing all around.
Now, Brad, next up this week, an international team of astronomers has challenged a popular theory about dark matter dominating gravity in the inner parts of galaxies like the Milky Way.
Yeah, and so, what they're really trying to figure out is where exactly does the distribution of dark matter in a galaxy lie? And so this is done by Ken Freeman and his PhD student, Ken Freeman being one of the people along with Vera Rubin and others, to actually show that dark matter is a real thing. And he's been working on this for the better part of 50 years. And new technologies and telescopes have really allowed him to kind of pinpoint the distribution of mass inside our own Milky Way. Really, where is the luminous mass, the stuff that we say, the normal stuff contained, and therefore by measuring the rotation, the speed, and therefore the mass of our galaxy, where likely is the rest of the dark matter, and finding that really visible matter, as it's called, dominates the inside. And it looks like dark matter is really just contained more to the outside of our Milky Way.
And that really goes to how the shape of the galaxy is formed, and I guess sort of maintains over the millennia. Why was the sort of thinking that dark matter was in the center?
We always knew that there was more luminous mass in the centers, and as you went to the outside, that's where you see dark matter. The issue slightly is observational, right? You're more dominated by stars and gas and stuff towards the center, less towards the outside. So you're more likely to see the effects of dark matter towards the outside of a galaxy rather than the inside. So by being able to actually pinpoint how much there is on the inside, you can actually get a better understanding really of where that distribution lies. So it's as much as really figuring out what is on, a kind of an inventory of towards the insides of the galaxies. We're not even talking about just the exact inside where the supermassive black hole is. We're talking about tens of thousands of light years within the center, because these dark matter distributions and what we call the dark matter profiles, where dark matter lies, goes out way far beyond what appears to be the galaxy where most of the light and gas is. And so it's really trying to show just how dark matter clumps, how dark matter interacts with normal matter, and how that comes to form, as you say, actually, the evolution and shape and size of galaxies.
Now, the team needed to pick a galaxy that was similar to the Milky Way to study spiral galaxies, to understand our own galaxy, and they chose NGC 6946, which is about 22 million light years away from Earth. I guess the biggest thing here, Brad, is to not be standing on the inside looking out, but standing on the outside looking in.
Yeah, look, because you will always be slightly obscured, blocked by stuff our own galaxy. So doing some of these things in our own galaxy is always tricky. So you need to find similar analogs, and we can do this based on measuring the parts of the galaxy. We can see how it moves, where the stars are, and looking at those analogs in the nearby universe. And again, really focusing on the motions of spiral galaxies. And by looking on the outside, so to speak, you can get the whole picture of a galaxy, where it's going to be always impossible to do that in our own Milky Way because we're in the middle of the thing.
Well, the group designed and built a specialized piece of equipment, the Planetary Nebula Spectrograph, and that was mounted on the William Herschel telescope in the Canary Islands. Really specialist equipment to look at this specialist part of astrophysics.
Yeah, and so really focusing on finding planetary nebulae. So these are after a massive star, a low mass, a small star kind of puffs out like our sun. It generates and pushes this big, beautiful nebula with a white dwarf on the inside. Now, planetary nebulae are pretty easy to find, but because they emit lots of certain gas signatures, you can measure that gas, figure out exactly how fast that gas is spinning, therefore how fast it's moving around the galaxy. And they're pretty bright and easy to identify, and there's usually quite a lot of them. And they, from what we understand, based on the types of stars, are kind of all across the galaxy. So, some types of stars clump together in different parts of the galaxy, whereas these we can find fairly evenly distributed across the entire span of a galaxy, which means they're a good probe of looking at the entire galaxy rather than a segment like other probes.
You can get social with Trekzone. Australia's unofficial home of Star Trek is everywhere you are. Just search for Trekzone.
And last up this week, Brad, in a series of breakthrough papers, theoretical physicists have come close to redefining what we think we know about black holes.
Yeah, this goes back to what we call the black hole information paradox. And this has been around really, pre-Stephen Hawking and that sort of thing, Hawking radiation, right? This idea that there is some information that leaks, so to speak, out of a black hole. And this issue has been around for the better part of, 5-6 decades, well into the 70s. What is actually happening here? Now, Stephen Hawking and colleagues have had attempts at the solutions, and the question was, is their solution the complete answer or kind of an approximation, so to speak? And it really has to do with how gravity, and because these things are such strong in terms of gravity, behaves with what we call quantum mechanics, and that is the laws governing basic particles, the basic fundamental building blocks. And this is a big issue, is trying to combine these two things and to get them to work. And so a new team has had a nail at this to figure out, if we calculate and how these things come together, why do black holes leak a bit of stuff back into our universe?
It's a very peculiar one. But what do we mean by information coming or leaking out of the black hole? What is the information?
Yeah, so when we say information, we're not just, talking about like there's this big message or something that comes into it. We're really talking about fundamental particles, again, what we call quantum mechanics and the properties of those quantum mechanics. When you look at a particle, it has certain properties, and it has certain levels of, even that basic level, energy, what's called Hawking radiation. And Hawking radiation is not necessarily what you think of normal radiation, so to speak, but anything that emits energy emits radiation. You emit radiation technically a little bit. Bananas do, all sorts of things. And so this idea is that a bit of this stuff, the properties of what the particle can exist, eventually kind of escapes or seeps out and kind of devolves almost. So that, the properties that define what makes a thing eventually can just de-evolve, almost like de-evolution, into just one basic thing that is always kind of governed by the black hole. So instead of being able to have a wide variety of particles that have their own different properties and their own different things that make them up, the black hole eventually sometimes spits out some of these options and makes what goes into a black hole or becomes into a black hole like a boring thing. So it takes away the variety of life.
Well, according to Einstein's general theory of relativity, the gravity of a black hole is so intense that nothing can escape it. So we're sort of redefining, as we learn more about the universe, what we think we know about the universe.
Yeah, and this is really the trick, is we know quantum mechanics exists. This is what governs the quanta, the things that make up the things that make up the things that make up the protons that make up the atoms. And then we have gravity. And we know gravity exists, but we don't know what gravity is fundamentally. We know it's a force, but what is actually causing gravity in space-time? And this is where Einstein's general theory of relativity is this is what space-time is. So it's trying to use gravity and Einstein's theory, relate it to what quantum mechanics says, because this is where this intersection is happening. You get these extreme boundaries of gravity in Einstein's equations. You then have a different set of equations which says how governs the basic building blocks of laws. How do you join them together? And that's the problem. How do those things come together? And this is a big issue in science, and getting towards this idea of the grand unified theory, this idea that all of these calculations, all of these equations really fit into one single point at some point. Others say, well, there's quantum gravity, which is a different take of this. This new solution is trying to improve upon what Hawking did, and they kind of funnily described it as kind of like a series of sticky tape with string, really trying to patch these things together to get it to work. And, it's a very delicate bridge that if something falls on it, it'll break apart. And it's a really hard thing to try and get these two extreme parts of the universe to work together, because we know funny things happen at this level.
And they are such a mystery, these black holes, that we think we've sorted everything out with how we think everything works. And then something like this is thrown up and throws things into chaos, and then we try and explain it away, but then something else comes along and creates it up. And I'm just reading this article you sent for background from Wired, talking about heated debates in Zoom calls and webinars as the effects of the pandemic hit us. They hit even the scientists and the astrophysicists working on this, that they've got to resort to Zoom calls. I can just imagine, we're in a Zoom call now here recording Talkin Science. Just imagine 20 of them together. Is it worse when they're in the same room together?
Hard to say. I've seen people literally in a meeting run to their office, come back with a piece of paper, and start banging on the chalkboard, showing that the other person was wrong. So you just don't get that same effect with Zoom.
Have you ever encountered a situation similar to that?
Oh, yeah. But, and look, it is an important thing, and they do this great example, right? If you send 100 kilos of an astronaut into a black hole, the black hole grows by 100 kilos just about. But if eventually over time, when that radiation is leaked back, Hawking radiation, none of that 100 kilos can be identified or traced to being even related at the fundamental level to an astronaut. Like, it's kind of like, you throw in something into a shredder, and all of a sudden the shredder doesn't just shred it, it just melts it, mixes it around, and puts it into a new ball, and then re-shreds that out and spits it back out. You just have no idea where it came from. And so the question is, what is this churning and why inside a black hole? And it's actually very fundamental for trying to understand what happens in a black hole, and how they grow it, and why they leak out this information, Hawking radiation, as they do, and why that radiation or information leaked out. It's just complete nonsense. And it's a very fundamental part. As we start to understand more, a lot of what we talked about why black holes behave the way they do.
So I think in conclusion, Brad, the theory of black holes no longer contains a logical contradiction that makes it paradoxical. So if I can't even rely on black holes being black holes anymore, what can I rely on?
Exactly. That's right.
Well, fantastic, Brad. It's been fun to pick apart the stories of the week with you, as we do every week here on Talkin' Science. 101 episodes down now. It is incredible that we're talking science. So there is so much going on that we can talk about.
Yeah, and we'll keep going next week.
Absolutely will, and we will catch you then.
Thanks.